The story of Isaac Newton does not begin in a palace or a wealthy household. Instead, it starts in a place filled with silence, absence, and loneliness. On December 25th, 1643, in a small village called Woolsthorpe in England, a child was born whom no one imagined would one day change the way the world thinks. Newton was born prematurely, so weak that many believed he would not survive. His body was fragile, his breathing faint, and life itself seemed to test him from the very first moment. Even more painful was the fact that Newton's father had died before he was born. From the day he opened his eyes, he never experienced the presence of a father. After some time, Newton's mother remarried and left to live with her new husband. Young Isaac was left behind in the care of his grandmother. This was the moment when loneliness quietly entered his life. Childhood is usually a time of warmth, affection, and protection, but Newton received very little of that. He grew up without his parents, surrounded more by silence than love. He rarely spoke, often sitting quietly, observing the world as if he were trying to understand something deeper than words could express. While other village children spent their days playing and running around, Newton was usually alone. He watched the soil, stones, wind, and the movement of objects with intense focus. Sometimes he would sit on rooftops, staring at the clouds, and at other times he would observe objects falling to the ground. People thought he was strange or slow, but in reality his mind was full of questions most people never think to ask. This was the foundation of the extraordinary scientist he would later become. Newton's childhood was not filled with joy, but with thinking and feeling. He disliked noise and crowds and preferred silence. Yet this solitude did not weaken him. Instead, it strengthened him from within. He quietly observed the world, trying to connect ideas and patterns in his mind. At an age when most children are only interested in play, Newton's mind had already begun to work deeply and independently. During his early school years, Newton did not stand out as a brilliant student. He was neither the top of his class nor a teacher's favorite. However, what set him apart was his deep thinking and his stubborn determination to understand things. If he understood a concept, he never forgot it. And if he did not understand something, he could not rest until he did. This stubborn curiosity later became the greatest weapon of his life. The lack of affection, the distance from his mother, and the emotional neglect he experienced created an inner world where Newton relied only on his thoughts. This is why, as he grew older, loneliness no longer frightened him. It empowered him. Where others felt uncomfortable being alone, Newton produced his greatest ideas. By the end of this chapter, it becomes clear that this quiet, fragile, and lonely child was hiding a storm within him. A storm that, when the time came, would shake the foundations of human understanding. Isaac Newton's school life was not the story of a child who was immediately recognized as brilliant. In fact, for many years it was the opposite. When Newton first attended school, he did not stand out in any extraordinary way. He was quiet, withdrawn, and physically weak compared to other boys. In classrooms filled with noise, competition, and discipline, Newton blended into the background. Teachers did not expect greatness from him, and classmates did not see him as special. He was simply another student, often ignored, sometimes underestimated, and rarely understood. In those early years, Newton struggled to find his place. He was not naturally confident, nor was he socially strong. Other students were louder, more aggressive, and more competitive. Newton often found himself pushed aside, mocked, or treated as insignificant. These moments of humiliation left deep emotional marks. Yet instead of breaking him, they planted something powerful inside him, a quiet determination to prove, first to himself, that he was capable of more. Newton's turning point came not through encouragement, but through conflict. One day, after being publicly humiliated by a classmate, something inside him changed. That moment of insult awakened a fierce inner resolve. Rather than responding with anger or violence, Newton chose a different path. He decided that he would rise above others not through force, but through mastery of knowledge. From that day forward, learning became his battlefield. He began to study with an intensity that surprised everyone around him. While other students studied only to pass exams, Newton studied to understand. He read beyond what was assigned, revisited lessons repeatedly, and questioned ideas others accepted without thought. His memory was sharp, but more importantly, his reasoning was deep. Slowly, almost silently, Newton began to climb to the top of his class. Those who once ignored him now watched in confusion as he surpassed them. Yet academic success did not make Newton socially comfortable. Even as his grades improved, he remained distant and isolated. He did not seek friendship or approval. Instead, he found satisfaction in solving problems and understanding principles. Books became his closest companions. In reading, he found clarity. In thinking, he found peace. The classroom, once a place of discomfort, slowly became a space where his mind could stretch and grow. Newton was especially fascinated by mathematics. Numbers made sense to him in a way people did not. Where human relationships felt confusing and unpredictable, mathematics felt pure, logical, and honest. Each problem had an answer, each equation a solution. This certainty gave him confidence. It was here that his mind began to show signs of extraordinary power. At home, Newton continued his habit of isolation. He spent hours alone, sketching ideas, writing notes, and experimenting with simple tools. He built small machines, drew diagrams, and explored concepts far beyond his age. No one guided him. No one praised him. His growth was self-driven, fueled by curiosity rather than reward. What is remarkable about this period is that Newton's genius did not emerge from comfort. It emerged from pressure. Rejection taught him independence. Humiliation taught him discipline. Silence taught him focus. While others relied on external validation, Newton learned to rely entirely on his own standards. This inner discipline would later allow him to work for years without recognition, driven only by the desire to understand truth. By the time Newton finished school, he was no longer the weak, unnoticed boy he once was. He had transformed quietly, without celebration. His teachers now recognized his ability, though they could not fully grasp its depth. His classmates saw his intelligence, but not his future. What they did not realize was that Newton's mind had already outgrown the limits of the classroom. When Isaac Newton entered Trinity College, Cambridge University, in 1661, it did not feel like the beginning of greatness. In fact, it felt like another uncertain step in a life already filled with quiet struggle. Newton did not arrive as a confident scholar or a celebrated student. He came from a modest background, socially awkward, emotionally distant, and still largely unnoticed by the world. Cambridge, at that time, was a place of tradition, hierarchy, and rigid thinking. Knowledge was passed down through authority, not questioned through curiosity. For a mind like Newton's, this environment felt limiting rather than inspiring. University life demanded conformity, but Newton's mind resisted it naturally. Lectures were based on ancient ideas that had been accepted for centuries without challenge. Aristotle's philosophies dominated the classrooms, and questioning them was often discouraged. While other students memorized what they were taught, Newton quietly sensed that something was missing. He felt that truth could not belong only to the past. It had to be discovered again through observation and reasoning. This quiet disagreement marked the beginning of his intellectual rebellion. Newton was not a wealthy student. To support himself, he worked as a sizar, performing small tasks for richer students in exchange for reduced fees. This position placed him at the bottom of the social ladder. He lived modestly, spoke little, and avoided unnecessary interaction. Yet this lack of comfort gave him something invaluable: time alone. In his small room, late at night, under the dim light of a candle, Newton read endlessly. He did not limit himself to university textbooks. Instead, he explored the works of Galileo, Kepler, Descartes, and other thinkers who dared to question accepted knowledge. This period marked a critical transformation. Newton was no longer just learning. He was teaching himself how to think. He compared ideas, challenged assumptions, and built mental connections others overlooked. Mathematics became his strongest language. Through numbers and symbols, he found a way to describe reality with precision. While others saw math as a subject, Newton saw it as a tool, a key to unlock the hidden structure of nature. What truly set Newton apart during his Cambridge years was his independence of thought. He did not wait for permission to explore new ideas. He wrote his own notes, developed his own methods, and pursued questions that fascinated him personally. Many of these ideas had no immediate practical value and earned him no praise, but they shaped the framework of his future discoveries. Newton was laying intellectual foundations without realizing how powerful they would become. Emotionally, Newton remained distant. He formed few relationships and showed little interest in social life. His world revolved around thinking, writing, and reflecting. Loneliness, which troubled others, felt natural to him. In solitude, his concentration deepened. He could think for hours without distraction, following a single idea through layers of complexity. This ability to sustain deep focus would later allow him to solve problems that others could not even clearly define. Cambridge did not guide Newton toward discovery. It simply provided the space where his mind could grow freely. The university taught him structure, but self-learning gave him vision. He began to realize that true knowledge does not come from repeating old ideas, but from questioning them. This realization quietly reshaped his identity. Newton was no longer just a student. He was becoming a thinker. By the end of this phase, Newton's notebooks were filled with original thoughts, sketches, calculations, and unanswered questions. None of this work brought him recognition at the time. In 1665, just as Isaac Newton's mind had begun to awaken to the possibilities of mathematics, physics, and astronomy, the world around him erupted in chaos. The Great Plague swept across England, closing universities and forcing students to leave their classrooms. Cambridge, normally filled with the sounds of debate, lectures, and scholarly life, fell silent. For most people, this would have been a moment of fear, confinement, and lost opportunity. For Newton, it became the most extraordinary period of his life, a time that would shape him into the scientist the world would never forget. Newton returned to his family's estate in Woolsthorpe, a small village miles away from the academic halls of Cambridge. Here, isolated from peers, mentors, and the structured life of the university, Newton faced a world reduced to quiet fields, empty rooms, and endless hours of reflection. The plague had created an environment that most would call restrictive, but for Newton, it was liberating. The absence of distraction allowed his mind to wander freely, exploring ideas that had been only half-formed before. During these years of isolation, Newton's genius began to reveal itself in ways no one could have predicted. He observed the simplest things in nature, the falling of an apple, the motion of a pendulum, the reflection of light, and began to ask questions that would eventually redefine human understanding of the universe. He pondered the reasons behind gravity, motion, and celestial movement. Unlike most, he did not see the world as chaotic or random. He sensed patterns, order, and invisible forces guiding every action. It was in these quiet days, amidst the loneliness imposed by the plague, that Newton began to formulate the ideas that would become his laws of motion and universal gravitation. The isolation also provided Newton with uninterrupted time for experimentation. He dissected light through prisms, explored the mathematics of motion, and developed rudimentary tools to test his theories. Nights were spent under candlelight, poring over notes, performing calculations, and challenging assumptions. Days were spent walking through orchards, observing apples fall, the sway of branches, and the flight of birds. Each observation, no matter how small, became a piece of a puzzle he was slowly assembling. While the outside world panicked and struggled for survival, Newton's mind was creating a framework for understanding the universe. Emotionally, these years were intense. Newton was alone, but not lonely in the traditional sense. His isolation was purposeful, chosen, and productive. Solitude became a laboratory for thought. In these long, silent hours, he wrestled with questions that had no immediate answers. He questioned everything: the nature of light, the motion of planets, the very laws of existence. Each question was a spark, each unanswered problem a fire. Few humans in history have experienced such concentrated intellectual growth under conditions of fear and uncertainty. Yet Newton thrived where others would have merely survived. It was during the Plague Years that Newton began to sketch the early outlines of calculus, the mathematical system that would later allow him to describe continuous change and motion in precise terms. He explored infinite series, limits, and rates of change, ideas that even today form the backbone of advanced mathematics, engineering, and physics. At the same time, he developed the conceptual foundations for his laws of motion, laying the groundwork for a scientific revolution that no one could foresee at the time. During his time in isolation at Woolsthorpe, Isaac Newton's attention was drawn again and again to the ordinary events of nature, events so common that most people never stopped to question them. Among these was the simple act of objects falling to the ground. Apples fell from trees, stones dropped from hands, rain descended from the sky. For centuries, people had accepted this behavior as natural and unquestionable. Newton, however, was not satisfied with acceptance. His mind demanded explanation. He did not ask what happens, he asked why it happens. One quiet day, as Newton sat reflecting in the orchard near his home, he observed an apple falling from a tree. The moment itself was not magical, dramatic, or unusual. Apples had been falling for as long as trees had existed. What made this moment extraordinary was not the apple, but the mind observing it. Newton did not see a simple fall. He saw a mystery. Why did the apple fall straight down instead of sideways or upward? Why did it move toward the earth? And if the earth could pull an apple toward itself, could that same force reach much farther? This question marked a turning point in human thought. Newton began to imagine that the force pulling the apple downward was not limited to objects near the ground. He wondered whether this same invisible force extended beyond the earth, reaching the moon, the planets, and even the distant stars. This idea was radical. Until then, many believed that different rules governed the heavens and the earth. Newton challenged this separation. He proposed that the universe might be governed by a single, universal force. As Newton reflected deeper, he began connecting ideas he had been developing for years. He considered the moon's orbit around the Earth and questioned why it did not simply fly away into space. What held it in its path? Could the same force that pulled the apple downward also be responsible for holding the moon in its orbit? The simplicity of this idea was powerful. It suggested that nature followed consistent rules, no matter how large or small the scale. Newton did not rush to conclusions. His mind worked slowly, carefully, and relentlessly. He turned to mathematics, using the early forms of calculus he was developing to test his ideas. He calculated distances, forces, and motion, searching for patterns that could confirm his intuition. Every calculation brought him closer to a breathtaking realization. The force of gravity weakened with distance, but never disappeared. It reached everywhere. This was not just a scientific insight, it was a philosophical one. Newton was proposing that the universe was orderly, predictable, and governed by laws that the human mind could understand. The apple was no longer just fruit falling from a tree. It became a symbol of unity between earth and sky, between the ordinary and the cosmic. Through gravity, Newton connected the smallest object to the largest celestial bodies. Emotionally, this discovery was overwhelming. Newton was not celebrating loudly or seeking attention. He worked in silence, aware that his ideas challenged centuries of belief. He understood that such a claim required absolute precision. Doubt drove him to refine his calculations again and again. He questioned himself as fiercely as he questioned the universe. This relentless self-criticism strengthened his theory rather than weakening it. Newton's concept of gravity was revolutionary because it replaced mystery with understanding. Where people once saw divine intervention or unknowable forces, Newton saw measurable laws. He described gravity not as magic, but as a natural force acting between masses. This shift transformed science forever. For the first time, humanity had a framework to explain why planets move, why tides rise and fall, and why objects behave the way they do. Yet, despite the magnitude of his discovery, Newton kept much of this work private for years. He was cautious, aware that presenting such ideas required flawless reasoning. The world outside Woolsthorpe remained unaware that a universal law was being born in silence. While society struggled with disease and uncertainty, Newton was uncovering a force that governed the entire cosmos. The story of the apple has often been simplified, even mocked, but its true power lies in what it represents: the courage to question the obvious. Newton taught the world that greatness does not come from extraordinary events, but from extraordinary attention to ordinary events. The apple did not make Newton great. His willingness to think deeply did. By the end of this period, Newton had laid the foundation for the law of universal gravitation, a concept that would later become one of the cornerstones of modern science. He had unified earth and sky under a single principle, revealing that the same force guiding falling apples also directed the movement of planets. This insight changed humanity's place in the universe forever. This was not yet public success, nor widespread recognition. It was quiet triumph, a victory of thought over assumption, of curiosity over tradition. In the stillness of Woolsthorpe, Isaac Newton had discovered a truth so powerful that it would echo through centuries, shaping science, technology, and human understanding itself. After laying the foundation of gravity in his mind, Isaac Newton turned toward a deeper and even more fundamental question: how exactly do objects move? Motion was everywhere: stones rolling down hills, carts pulled by horses, planets circling the sun. Yet no one had ever described motion in a clear, universal, and mathematical way. For centuries, people relied on ideas inherited from ancient philosophers, explanations based more on logic and belief than on measurement and proof. Newton sensed that something was missing. Nature, he believed, spoke a precise language, and that language could be discovered. Newton began observing motion not as a collection of separate events, but as a system governed by consistent principles. He watched how objects behaved when pushed, pulled, or left alone. He asked simple but profound questions. Why does a moving object eventually stop? What determines how fast something accelerates? Why does every action seem to produce a reaction? These were not questions meant for debate. They demanded exact answers. Working in isolation, Newton slowly shaped what would become his 3 laws of motion. These laws did not emerge all at once. They formed gradually, refined through observation, calculation, and relentless thought. Newton tested his ideas mentally again and again, imagining ideal situations where friction, air resistance, and imperfections were removed. In these simplified worlds, patterns became clear. Motion, he realized, followed rules that applied everywhere, to everything. The first law revealed a truth that seemed simple but was deeply revolutionary. An object at rest remains at rest, and an object in motion remains in motion, unless acted upon by an external force. This idea challenged centuries of belief. People once thought that motion required constant force. Newton showed that rest and motion were natural states. It was resistance, not motion, that required explanation. This insight reshaped humanity's understanding of the physical world. The second law brought mathematics into the heart of motion. Newton demonstrated that the change in motion of an object depends on the force applied and the object's mass. With this, motion became measurable, predictable, and calculable. For the first time, people could calculate exactly how much force was needed to move an object, how fast it would accelerate, and how its mass influenced its behavior. The universe was no longer vague. It was numerical. The third law completed the picture with elegant symmetry. For every action, there is an equal and opposite reaction. This principle explained balance in nature. When a foot pushes against the ground pushes back, allowing movement. When a cannon fires a cannonball forward, the cannon recoils backward. Newton showed that forces never exist alone. They come in pairs, maintaining harmony in motion. What made these laws extraordinary was not just their accuracy, but their universality. They applied equally to a falling apple, a sailing ship, a galloping horse, and a distant planet. Newton had done something no one before him had achieved. He had unified the physical behavior of the entire universe under a small set of principles. Motion was no longer mysterious. It was governed by rules that could be learned, tested, and used. Emotionally, Newton understood the weight of what he was discovering. These laws did not merely explain motion. They replaced centuries of misunderstanding. Yet he remained cautious. He refined his ideas repeatedly, testing them against every example he could imagine. He was not interested in being partially right. He demanded certainty. The laws of motion also revealed something deeper about Newton himself. They reflected his personality, precise, disciplined, and uncompromising. Newton believed that truth was not shaped by opinion, authority, or tradition. It was shaped by evidence and reason. This belief would later put him in conflict with others, but it also made his work unshakable. With these laws, Newton created a new language for science, a language of forces, mass, acceleration, and interaction. Engineers, astronomers, and scientists would later use this language to build bridges, design machines, predict planetary motion, and eventually send spacecraft beyond Earth. Every moving system, from the smallest mechanism to the largest celestial body, could now be understood through Newton's framework. At this stage, Newton still kept much of his work private. He was aware that such revolutionary ideas would invite criticism and debate. Yet internally, he knew something extraordinary had been achieved. He had transformed motion from a subject of philosophical discussion into a precise science. By the end of this period, Isaac Newton had not only discovered gravity, but had also given humanity the tools to understand how forces shape movement throughout the universe. The laws of motion became the backbone of classical physics, standing firm for centuries and influencing every scientific advancement that followed. This was not just a scientific breakthrough. It was a shift in how humans understood reality itself. Motion was no longer mysterious or chaotic. It was ordered, governed, and knowable. And at the center of this transformation stood a quiet, solitary thinker who believed that the universe, when carefully observed, always reveals its rules. As Isaac Newton pushed deeper into the mysteries of motion and gravity, he encountered a problem that threatened to stop him entirely. The existing mathematics of his time was simply not powerful enough to describe continuous change. Geometry could describe shapes, and arithmetic could handle fixed quantities, but the natural world was dynamic. Objects accelerated, curves bent smoothly, and forces varied from moment to moment. Newton realized that to explain nature accurately, he would need a new kind of mathematics, one that did not yet exist. This realization did not come as a sudden inspiration, but as a growing frustration. Newton could see the answers conceptually, but he lacked the language to express them precisely. How fast does something change at a single instant? How can motion be measured at a specific moment rather than over a long period? These questions haunted him. For most thinkers, such limitations would have marked the end of inquiry. For Newton, they marked the beginning of invention. Working alone, often through the night, Newton began to construct a new mathematical framework from scratch. He approached the problem with his characteristic intensity, breaking it down into its simplest components. He imagined quantities that flowed rather than remained fixed. He thought of motion not as a series of steps, but as a continuous process. In doing so, he created what he called the method of flux science, a way to describe how quantities change over time. This new mathematics allowed Newton to calculate instantaneous rates of change, what we now call derivatives, and to measure the accumulation of quantities over time, what we now call integrals. With these tools, Newton could finally express the laws of motion and gravity with exact precision. Motion became measurable at every instant. Curves could be analyzed point by point. Nature, once elusive and fluid, became mathematically transparent. The creation of calculus was not merely a technical achievement. It was a mental revolution. Newton had extended the reach of human thought, enabling people to describe processes that were previously beyond calculation. Rivers flowing, planets orbiting, objects accelerating. Everything could now be expressed through a unified mathematical language. This language did not simplify nature by ignoring its complexity. It embraced complexity and made it understandable. Emotionally, this period was intense and isolating. Newton rarely shared his work, even with those closest to him. He feared misunderstanding, criticism, and premature exposure. He held himself to an impossible standard, revising his methods repeatedly, refining definitions, and testing results against reality. His notebooks filled with dense calculations, symbols, and ideas that few people at the time could comprehend. Genius, for Newton, was not a gift. It was a burden. Calculus also revealed Newton's unique relationship with necessity. He did not invent it to gain fame or recognition. He invented it because he needed it. Nature demanded a new language, and Newton answered that demand. This practical motivation gave calculus its power. It was not abstract mathematics created for beauty alone. It was mathematics forged to explain the real world. Years later, this achievement would place Newton at the center of controversy, especially with the mathematician Gottfried Wilhelm Leibniz, who independently developed a similar system. But during this moment in Newton's life, there was no rivalry, no public debate, only a solitary mind wrestling with infinity, motion, and change. The world remained unaware that one of the most important mathematical tools in history had just been created in silence. The impact of calculus would be vast and lasting. Engineers would use it to design machines and bridges. Scientists would use it to understand electricity, magnetism, and thermodynamics. Astronomers would use it to predict planetary motion. Centuries later, calculus would become essential to economics, medicine, computer science, and artificial intelligence. What began as Newton's private solution to a personal problem would become a foundation of modern civilization. Yet Newton himself remained cautious. He published little about calculus during his lifetime, preferring certainty over speed. He believed that truth should be released only when it could withstand the strongest scrutiny. This restraint delayed recognition, but preserved the integrity of his work. Newton was not racing against others. He was racing against error. By the end of this phase, Isaac Newton had achieved something unprecedented. He had not only discovered laws governing motion and gravity, but had also created the mathematical language needed to describe those laws precisely. Few individuals in history have shaped both the questions and the tools used to answer them. Newton did both. This was the moment when his genius reached its fullest expression. He had turned necessity into invention, frustration into insight, and isolation into creativity. Calculus was more than mathematics. It was proof that the human mind, when driven by curiosity and discipline, could extend its reach into the deepest structures of reality. As we reach the end of Isaac Newton's extraordinary journey, it becomes clear that his success was not built on talent alone. It was built on patience, isolation, discipline, and an almost painful dedication to truth. Newton did not live a life filled with applause or comfort. Much of his greatest work was done in silence, away from crowds, driven by questions that refused to leave his mind. His success was not sudden. It was earned through years of relentless thinking. Newton began as a quiet, uncertain child, far removed from the image of greatness. There were no signs that he would one day redefine science. He struggled with loneliness, insecurity, and deep internal conflict. Yet instead of allowing these struggles to weaken him, he turned inward. He transformed solitude into focus, curiosity into discipline, and doubt into determination. This transformation was the true foundation of his success. What makes Newton's story timeless is not just what he discovered, but how he discovered it. He questioned everything. He refused to accept ideas simply because they were old or widely believed. Whether it was motion, gravity, light, or mathematics, Newton demanded proof. He believed that nature followed laws, and that the human mind, if trained carefully enough, could uncover them. This belief became his guiding force. His achievements reshaped the world in ways that are still felt today. The laws of motion became the backbone of engineering and mechanics. Gravity connected Earth to the heavens, uniting the universe under a single principle. Calculus provided humanity with a new language to understand change, growth, and movement. And the Principia became one of the most important books ever written, influencing science for centuries. Yet despite all this, Newton remained deeply human. He was flawed, emotional, and often difficult. He struggled with criticism and feared being misunderstood. He guarded his work closely and avoided confrontation whenever possible. These imperfections do not diminish his greatness. They make it real. Newton's success did not come from perfection. It came from persistence. One of the most powerful lessons from Newton's life is that success does not always look glamorous. There were no grand celebrations during his greatest discoveries. No instant recognition. Often, there was only a man, a candle, and a notebook filled with calculations. Success, in Newton's world, was the quiet satisfaction of understanding something no one had understood before. Newton once said that if he had seen further, it was by standing on the shoulders of giants. But history shows that he became one of those giants himself. His work did not end with him. It became a foundation upon which future generations built their ideas. From space travel to modern technology, from engineering to artificial intelligence, Newton's influence continues to move the world forward. His journey teaches us that true success is not about speed, fame, or approval. It is about depth. It is about committing fully to a purpose, even when the path is lonely. It is about trusting curiosity and allowing discipline to turn questions into answers. Newton's life reminds us that the greatest revolutions often begin quietly, inside a single mind. As this story comes to a close, Isaac Newton stands not just as a scientist, but as a symbol of human potential. He showed that the universe is not chaotic, it is understandable. That knowledge is not limited by background or circumstance, but by the courage to ask questions and the patience to seek answers. And perhaps the most powerful truth of all is this: Newton's success was not the result of a single moment of brilliance, but a lifetime of thinking deeply when others stopped. His legacy reminds us that within silence, curiosity, and persistence lies the power to change the world.